Today we're going to continue learning about Chapter 5, Plate Tectonics and Earth Structures. This is Lesson 2, Plate Tectonics, a Unifying Theory. Our agenda for today is a brief review of Lesson 1. We talked about Earth's moving plates. You're going to learn some new vocabulary words, and our topics for discussion are: how do scientists study Earth's structures? What are the main layers of Earth? How are the main layers of Earth subdivided? What moves the plates? What is plate tectonics? What is a unifying theory? And finally, you'll get your assignment. So we're going to review just briefly what we learned in Lesson 1. We talked about continental drift, and this is the theory that the supercontinent, Pangea, remember when all the continents were smushed together, it broke apart over 2 million years ago to eventually form the continents we have today. As the continental plates move apart, mid-ocean ridges are formed. As they move together, oceanic trenches are formed, and we're going to talk more about that today. The plates are always moving, and this movement causes earthquakes and volcanic activity. And this is for a future lesson, but I want you to start thinking about it. If you look along the coastline, you'll notice that there's a lot of volcanoes and earthquake activities. You can also see the outlines of the plates, which we're going to talk more about. So some new vocabulary words you're going to come across: seismic waves, crust, mantle, core, lithosphere, semi-molten, asthenosphere, magma, lava, convective flow, plate tectonics, and subduction. I also threw in the word density that we'll come across later. So how do scientists study Earth's structures? Scientists use seismic waves. Seismic waves are vibrations that travel through the Earth. And there are two kinds of seismic waves: surface waves and body waves. And I'll get to those in a moment. I just want to point out this machine over here. This is called a seismograph, and it is used to detect, measure, and record energy waves from Earth movements, namely earthquakes and volcanoes, which we will get to in a later lesson, but I want you to be aware of it. So as I mentioned before, there are two types of seismic waves. There's the surface waves, which are closer to the surface of the Earth. They're slower than the body waves. And if you can imagine ripples on a pond only going through Earth, that can get you thinking about surface waves. Body waves are located more in the interior, deeper into the Earth. And these come in two types: P waves and S waves. P waves are the primary waves, and they're faster than the S waves. They can travel through any kind of matter: gases, liquids, and solids, and this gives scientists and geologists a clue to what is inside of the Earth. As the P waves move, they'll push and compress or pull and stretch the materials in the Earth, and they cause vibration in the direction of movement. S waves are the secondary waves, and they travel only through solid material. They vibrate at right angles to the direction of travel, and the vibration moves materials up and down or left and right. What are the main layers of Earth? So remember, I talked about the word density, and this might be a new word for you, so I'm going to explain it. Density is the measure of how much material there is in a given space. So think about if you have a rock or stone and you have a piece of wood, a little wooden block, and they're the same size, and you decide to throw both of those into the lake. The rock is going to sink to the bottom because it is denser. It has higher density, which means the molecules in that rock are closer together, whereas the wood is going to float because the molecules are further apart, making it less dense. So the crust of the Earth is the outermost layer, and it's made of solid rock. Depending on where you are, it varies in thickness, and it goes from about 3.7 miles to 43.5 miles in thickness. Underneath that is the mantle. This is made of solid molten rock. Some rock can flow very slowly due to high temperatures and pressures, and the mantle is about 1,800 miles in thickness. The core is the very center of the Earth. You have the outer core, which is made of liquid, and the inner core, which is solid. The core is very dense, and it's composed mainly of iron and nickel. It's about the diameter of the core is about 4,300 miles. So if you were to travel from the west coast of the United States to the east coast, you wouldn't even get 4,300 miles. So it is very big when you think about that. How are the main layers of Earth subdivided? We have two kinds of crust in our Earth. We have the continental crust, which contains continents and land, and it's composed mostly of lightweight rock called granite. This is a volcanic rock. If you've been up in the mountains around here, you've seen granite. It's the white rock that has like flecks of black and gray in it. Kind of reminds me of salt and pepper. It's thicker and less dense than oceanic crust. The average thickness of continental crust is about 20 miles thick. Oceanic crust contains the ocean. It's mostly made of volcanic basalt. It's denser than the continental crust, and the average thickness is 4 to 5 miles thick. So if a scientist is going to get a core sample of the Earth or try to dig down, drill down into the mantle, this is a great place to do it. The mantle is located beneath the crust, and it's composed of two layers. The lithosphere, think about the word lithos, it's Greek for stone. So this is the rigid outer layer of the mantle. It's composed of semi-molten rocks. Semi-molten rocks are rocks that are almost melted and they're flexible. They can flow, bend, stretch, and compress. If you've seen anyone blowing glass or making things with glass, it's very similar to that, the way that the glass is really malleable or easy to shape. It's broken up into lithospheric plates that float on the asthenosphere. So the asthenosphere is right underneath the lithosphere. Asthenos is Greek for weak, and it is composed of molten rocks or magma. And the temperatures here are very, very hot, ranging from 650 to 1200 degrees Celsius. So remember, water boils at 100 degrees Celsius, so this is very, very hot. And just a side note, when magma rises to the surface, it becomes lava. Once it cools, hardens, and crystallizes, igneous or volcanic rocks are formed. And here's a picture of the structure of the Earth that I thought was kind of neat. It puts it into more of a perspective. So we have the atmosphere or the air around us, followed by the oceans and continents and the crust. Underneath that, we have the lithosphere and the asthenosphere. And then on this map, or sorry, this picture, they've broken it up to a lower mantle as well. So it shows you just how big this is. And then in the center, we have the outer core and the inner core. And you can look at that further on your own. What moves the plates? So plates move by convective flow. This is the continuous circular flow of materials as they are heated and cooled. If you see this example here, it's water boiling in a kettle. The water closest to the burner is warmer. Or hotter really. This is because the molecules are further apart, and so it's less dense, so it rises up to the top. And the closer it is to the surface, the cooler it's going to be. And then as the water gets cooler, the molecules start to move together, making it more dense. And then it falls back down and gets heated up again in a circle. Oh, sorry. And this is very similar to what we have on the inside of the Earth. So the closer to the core, the hotter it is, and then those materials flow through and then back down. What is plate tectonics? Plate tectonics is the theory that the surface of the Earth is made up of separate plates that move across the mantle. There are 7 large plates and around 12 smaller plates. And there are 3 types of boundaries that we're going to talk about. And you can see the boundaries along here. We're located on this North American plate. So the 3 boundaries are convergent, divergent, and transform. Convergent boundaries are where tectonic plates move toward or collide with each other. A subduction zone is the area where one plate is sliding underneath another plate. In my top example here, we have dense ocean crust, a dense oceanic crust subducting underneath the less dense continental crust. This is where you'll find deep ocean trenches and volcanic mountain ranges. So if you've ever been to the Oregon coast, those volcanoes along there, the Cascades, these were formed by this process. The second picture here shows oceanic plates subducting under an oceanic plate. So one of those plates will just sink underneath the other. And this is how volcanic islands and deep trenches are formed. Think the Caribbean islands. And then my last example here is the continental crust subducting under a continental crust. So the crust will buckle and it'll turn almost vertical, and very tall mountain ranges are formed, like the Himalayas of Asia. Divergent boundaries are formed when two plate boundaries move apart or away from each other. And here's a picture of underneath the ocean where seafloor spreading has happened with new crust forming. Divergent boundaries are almost always under the ocean, but there are a few on land divergent boundaries. And in this aerial view here, you can see the East African Rift Valley. You can see how it's cracking and falling and pulling apart. And on this map here, you see the east coast of Africa. And eventually, millions of years from now, this will actually be torn apart from Africa. And the Red Sea is in a complete divergent state. So the Arabian and African or Nubian plate have moved apart from each other, and it has filled in with ocean or with seawater. So the last kind of boundary is a transform boundary, and these are where plates are sliding past each other. And you'll find a lot of them on the ocean floor, but you do find some on land as well. And the San Andreas Fault in California is a transform boundary, and it's a great example of one. So if you see in this picture here, it starts in the Gulf of California and it moves up through California, Los Angeles, San Francisco. And as these plates slide past each other, that's what causes a lot of the earthquakes that we have in California. And then this picture here is an aerial view where you can actually see from above where the transform fault is. So what is a unifying theory? A unifying theory is a connection between theories to give a complete picture. Think of pieces to a puzzle. In our last lesson, we talked about Alfred Wegener and how he discovered continental drift. As this was combined with new findings like the 1960s discovery of seafloor spreading, the continents were shown to be more than just moving. So they're not just floating there. There's a reason. And thus, plate tectonics theories were formed. So scientists are still building on this. Why are the plates moving? What makes them move? So that's what a unifying theory is. So your assignment for this class is to write at least 3 sentences about each of the 3 layers of Earth. Remember, we have the crust, the mantle, and the core. Questions I want you to consider: where is the layer? Example, it is the top layer. What makes it different from the other layers? Example, it is made of solid rocks. For your assessment, or how I'm going to grade this, you may write, type, audio, video record your sentences, or you may draw, color, and label each layer with the name and a brief description. All right, thank you very much. In our next lesson, we're going to talk about earthquakes.